exponential functions were, power functions were ax to the b, whereas exponential growth, yeah, we're just going to do exponential stuff, so.
But it says the end.
Well, you know what I mean.
And
There.
you remove the functions.
Is that better?
There.
Yeah, but exponential
Yeah.
functions. Yeah, it is.
Now I understand what you're doing.
We're working with that model. Y equals a times b to the x. That's what we had for exponential functions. The telltale showing of growth versus decay was with that b value. It really doesn't make a whole big difference what your b value is here, but just so you remember, because it came up 6th hour a lot, that it was growth when b was greater than 1, and that it was between 0 and 1. This was growth. I don't remember if it was equal. This was your decay. The a value had no bearing, just meant whether it was a positive or negative growth. Positive, negative, excuse me, not positive, negative. It meant direction of the curve. That's all it was. Okay. It's no big deal. In these problems, we're dealing with b values that wind up being positive, so you don't have to worry about any negative things here. You could get a negative a. It's not a big problem. All we're doing is writing equations. Okay. So, when we did this a few years ago in this section, all we did was start out with an ordered pair set. If we know that this is an exponential function that goes through these 2 points, sorry, the snapshot I didn't go in there. If it goes through those 2 points, you basically are going to write the equation of ab to the x. Y equals ab to the x, knowing that one set of ordered pairs is 1, 6, and the other one is at 3 and 24. Just like we did last time when we had a system of equations, we're going to do the exact same thing, but this case it's a lot easier because there's no adding and subtracting. It's going to be direct substitution. Okay? So you just write it out in that first order pair. Your y value is 6, so that means that 6 has to equal a times b to the first power, and 24 has to equal a times b cubed. I'd say 9.5% out of 10 times you're going to use the first equation to get a by itself. It's rare that you use the second one. It doesn't mean you can't, but it's usually a lot easier to work with this with the one on the left.
No, it's really simple to solve because it's just 2 cubed times 3 equals 3.
Hold on. I'm sorry, what's that? Not value, what do you mean? No, it's, no, anything to the 0 power is 1.
That's exactly what.
When you're to the 1 power, you are yourself. Like 3 to the first power is 3 and so on. So here's what I'm doing. 6 divided by b is a. You okay with that? And now what we're going to do is just direct substitution. There.
Oh, okay. That's what you mean by you don't use the second equation.
Yeah. Because you're working with, you can simplify your degrees then. You wind up playing that game of war with your exponent rules from way back when. So if you have b cubed over b, what do you get? So b there.
B squared.
So divide out 6 and then square root.
Yes, sir.
Is it plus or minus?
No, like I said earlier, b values are always positive. Remember, your b values have to be positive because in order for it to be growth or decay, your b values are greater than 1 or between 0 and 1. That's the rule. That's why you don't have to worry about taking do plus minus exactly. Okay? So if b is 2, what's a? 3. And we come back here. So y equals a times b to the x. Your final answer would be y equals 3 times 2 to the x. And no, you cannot write 6 to the x. Okay? And that's it. Because it's bad. You're right. That's all it is.
So do we have to like graph these now?
Why? You got a calculator.
I feel like graph them in the calculator.
Well, all you had to do here was just write the equation.
The example is just like right now.
Yeah. Well, not yet.
So let's do homework. Okay, in this section.
So let's do it.
Eventually.
And this is where it takes you.
So, write the model. Write the equation. Write the equation. Mojo.
Jordan.
Mojo diagonally.
What's the next
You're bad.
So the answer is
Wait,
yes.
That's all, that's our answer for everything.
What?
Can I not the answer?
Oh, I'm not there yet. You're getting there.
Yeah.
There's Jordan has goals.
So he's turning the.
Yeah.
Scholarship for me. My dance skills. That is perfect.
Dude, I would move. I would not want to associate anything with that. It's a giant mess.
You're the one. The one part.
You got 12 for B, I hope?
Yep.
Okay. Which means you get what for A? Good. So Y equals 1/4.
That's a good one.
Okay.
I assume that they're going to be ones that is.
Eventually.
Yeah.
What we're doing, talk about the modeling of it. And this is where things get a little tricky. And this is where I want to make sure you guys understand how you're going to be able to use your calculator to show which model to choose from. So far when we've done our modeling, we've done linear, quadratic, cubic, polynomial ones, and then we did a little bit of that, and today we're starting exponential. Tomorrow we're going to talk about what's called logistic. And then on Wednesday we'll do trig. Each one of these modeling types is that you're going to have to be able to identify the model via the table. When you're looking at something graphically, as far as making sure something's linear, that's usually pretty obvious. It looks like a straight line. When we're looking at the polynomial ones, whether it was a squared term, a cubic term, a quartic term, whatever, remember how we were able to distinguish that via the table by doing that finite differences. Remember the devil always showed up, 666 every time with your differences? That's how you were able to figure out your degrees of those. Those are pretty simple to work themselves through. Well, what happens when it gets down to your exponential, and then tomorrow when we talk about logistics, it doesn't always show itself right off the bat like any of those other methods. So what we want to do is I'm going to show you guys a way to identify that it is exponential by proving that it works a certain method. So what I want to start with here is, I think most of you guys started going here, I want to create a table of L1 and L2. Okay? And I'll move this back up here in a second. Let's try to get the calculator out here as well to walk you through the same steps. Oops, sorry. Bless you.
Bless you.
Allergies are running random debate.
Yeah, they are.
With that edit.
Stat edit. My list here, I believe, starts at 1. I'm just going to,
1 to 10.
it's 1 through 10. Try to get it so it all shows up here. So L1 go 1 through 10. Okay. L2 1.6. Okay. Do you remember how to look at a scatter plot? How to go back to do that in the calculator? First thing you want to do is make sure that your stat plot is on. So hit second, y equals. Right now my stat plot is off, which means I have to hit enter to turn it on. When I hit enter, it gives me some options. It should be blinking on the cursor of on. Yours is probably already over there. I have to make mine move over. Now, the next one helps you pick the type of graph. I personally like using, this second graph. It gives you all the dots, but it's going to connect them. It's going to look more like connected dots. Okay. My x and y should default to the L1, L2, which is what we want. And now we go ahead and graph it. And you probably won't see much because your defaults are all sort of, your window's all out of whack. So, change your window. A lot of this stuff is going to stem from being able to adjust your window so you can visualize the data better. What should I set my x minimum to? 0. Just go 0 to 10. Now, my y minimum, I'm probably also going to set it at 0. And what am I going to put my maximum at? 50. Good. This is going to help give us a little bit better of an idea of what it looks like. And you get that. Everybody's looking kind of like that? Now, right off the bat, this kind of looks like it's an exponential function. It's increasing at an increasing rate. Well, in order to prove that it is exponential, there's one thing you do. To show it is an expo model, you want to plot x versus the natural log of y. If the graph of x versus the natural log of y is somewhat linear-ish, then it's exponential.
What is L and Y is a natural log?
Yes. And I'll show you how we can do this really, really fast in the calculator. And yes, that says linear-ish. What would linear-ish look like?
Straight-ish.
Straight-ish. Very good. If I take the x values via the natural log of y, it should look kind of like that. If it does, then it fits the idea that it's an exponential model. That's the trick to show exponential. Whereas the other ones, we did the polynomial where we did the finite differences. We do logistic ones tomorrow. There's a real subtle trick. And then when we do the periodicities of the trigonometric ones, it's also pretty.
Periodicity of trigonometric ones.
No, it's like if I was playing Scrabble, I would win.
So plot it in calculus?
Yeah, and I'll show you how to do it. Let's go back to your to your stat edit. And what I want to do is go to the L3 column. I'm not wiping anything out. Now, what I'm going to do here is I'm going to get all the natural logs of what was in L2. So all I have to do is type in natural log 1.6. Enter. Because it's right in front of me.
That makes me so mad.
Okay? If I type in natural log 2.7, I'm taking the natural log of all the numbers that are in my L2 column, and I'm just, the calculator, I don't have to write it out by hand because I can just type it in the calculator. Natural log. What was ever, right here, if you look, I'm at the third entry, so I'm gonna type natural log of 4.4. Okay?
I'm not the teacher.
What's wrong?
Thomas asked me what to do now, and I'm like,
Are you done, have you put all the natural logs in yet?
Yes.
Okay, like, just, what's wrong, Em? What's wrong, Em? So, once we get that whole column done, that L3 now has all of our natural logs, what was done in L2. So we've got all the natural logs stored. So I just want to graph that versus what was in L1. So I change my graph settings. So we hit second, y equals, and now I'm going to plot on the, let's try this. I haven't done this yet. Let's go to the second. I want to see if this works. Hit enter on plot 2. We're going to turn it on. No, we'll leave it on. I'm trying something here. I'm winging something here. I don't know if this is going to work.
Not safe.
It's not safe, but I don't think anything's going to explode. But what I'm going to change now is we have the second one is going L1 versus L2. I want to change that to L3. And this is how you do that. Put your cursor over it, and then hit second, number 3. Second, y equals?
No.
I go down to plot number 2. Hit enter. Turn it on, hit enter. And then move down. Oh, yeah. One more. Change that to L3 by hitting second. Okay. And then see down 3 seconds. There we go. Now, did it work? Did it show both on the same graph? It did. Sweet.
That's the nerdiest thing I've ever done.
It is kind of nerdy, but it didn't look as cool as I was hoping it would. Because the scale's all out of whack, so maybe it's not as cool.
Is that what it's supposed to look like?
It's wiggly.
No, it's. Oh, that's.
Yeah, it looks kind of.
How does
Yeah,
that
it's-
way look like?
Is that straight-ish?
It's straight-ish, but okay, it didn't look as cool as I'd hoped. So let's do this. We're not going to plot on the same stat anymore. So forget everything we just did in the past 90 seconds. We're going to plot it by itself. So go to second, y equals, turn off the first stat plot. Yep. And we're just going to plot. We're going to plot this one by itself, so there's just one graph on there. That's all we're going to do. We're going to graph them independently. Let's readjust our window. If we readjust our window, do I have to change my x, max, and mins? No, just my y values. I think the largest y value we got in L3 was like 3 point something. So I'm going to change it to 4. My y max, change your y max to 4 in your window.
Still the same with the line.
So if I look at it, that's pretty straight-ish, isn't it?
Yeah.
The only difference is that we've readjusted the scale to show that it's linear. Since this is linear-ish, we know it's an exponential model. Okay? Plus, it said it was exponential, so the problem. But anyway. Now, do you remember how to get the regression model out of this thing? Calculate, right? Again, all we're doing is pressing buttons on the calculator for a lot of this. So if we go back to our, stat, move over to calculate, we're looking for anything that says expo or exponential. You scroll through, yep, and that's it. X reg, or X reg.
Oh, man.
My first car was a Ford Escort EXP. It was awesome. I loved that car.
Or as you could say SS.
It was a two-seater coupe with a hatchback. It was awesome. Somebody has a red one out in the parking lot. It's awesome. I loved my EXP. It's probably the hot wire. It's really easy. So you hit enter. Your calculators, guys, your calculators don't have the upgraded operating system like this one does. It's going to, hold on, it's going to automatically default to looking at list L1 and L2. Okay? It's going to default to L1 and L2.
So how do we change that?
You don't have to worry about it because you're looking at it because you're looking at this model here to get the exponential. Okay, so this is fine. We tested that L3 to show it was linear-ish. So it's going to automatically dump back to L1, L2 for the model. Okay, so that gives you your A and your B value, which gives you your equation y equals 1.3 times 1.46 to the x.
Oh, I thought we were just go around the point like that.
2. I always do two decimals. Okay? So doing all of that, verifying that it's exponential, gives you a generic equation of that, which means you could, the table gives you the millions of years of cell phone subscribers from 88 to 97, or tease the number of years since 1987. I think the question was estimate when they had so many more cell phones. I don't know, whatever. Okay? But if you think about it, will this be always increasing, or is it ever going to plateau out? It's, right. At some point in time, you reach beyond your limited resources, and we'll talk about problems like that tomorrow because that's a logistic growth problem. It's going to constantly increase until it's going to tail itself off. I think who's in your bio, right?
Yeah.
Didn't you guys do something like that in like bacterium in a petri dish?
We haven't learned anything.
Okay.
Yeah.
It's true. So you've done stuff where bacteria are only going to grow and it's going to level itself off eventually.
Yeah.
That's a logistic growth problem.
We just
Where
did that.
it grows at an increasing rate and then it tails out.
Yeah.
We'll talk about that style, which is more real word than a constant growth rate. I mean, nothing's really have a constant growth rate. Well, I guess you can have money be a constant. Then eventually you wouldn't run out of money.
No, think about it. You can always make it.
You can always make more money too, so.
You've officially earned
You
all of
keep
the
planting
money.
trees. But if you're constantly planting trees, aren't you going to run out of resources to plant trees?
But then you're going to use old trees and plant new trees.
But you're gonna end up cutting down trees to make money anyways.
I guess you're right, because it could be a one-to-one. You cut a tree, plant a tree.
Yeah.
So it would be linear, wouldn't it?
If you could just add the trees.
It would it be constant? No, if it's one-to-one, you plant a tree. Cut a tree down, plant a tree.
Hey
Take one
guys,
out,
Katie
put
said
one
money's
in.
not made out of paper, so the tree argument is irrelevant.
Money's not made out.
Money's made out of water.
What about all the worms that they
Cotton fabric. It's a cotton fabric.
Yes! The Lorax!
This one time a tree got cut down in my neighborhood and I walked past this house.
My kids love that movie. It is. It's very good. It is very good. It's like that, they watched it Friday night, actually. I don't remember. And then it was Sneed, Sneed.
No,
Thaneed, that's right, Thaneed. Thaneed, not your Thaneed. I hurt my Thaneed because I'm missing my front tooth and I hurt my Thaneed. Questions on this? I will ask, yes ma'am.
Wait, can you hear something?
No, go ahead.
No, you might be answering the question.
No.
I was gonna ask like, what work on the show?
Exactly. This is why you're Okay. What happens a lot of times with these things, since you're in the exponential modeling section, it's going to be exponential. In order to show that it's going to work, what I want you guys, bless you, what I want you guys to get in the habit of doing, or better yet, when it comes down for test or quiz, which is, it might be Friday, it's starting to look like that. Yes, sir. We'll miss you terribly. We're not. I figured you won't be here on a Friday.
I'm going to judge some lights.
Now,
That sounds like a kind of.
do you bring the side of barbecue sauce right off the bat with you, knowing fair well that's what's going to happen? Do you just bring barbecue sauce with you?
What are you talking about?
You're gonna eat them.
No, I'm not. I'm going to like watch them. Watch people eat
That
them.
sounds.
So, are you going to go to Bovine University?
Actually, there's going to be more than calculator.
Hey.
Pigs as well.
Anyway, so, for example, like now if you're asking when we get back on track, so yeah, bring it off track. What happens is, I got a test or quiz, you're going to get a data set like this. You'd have to make the decision right off that, well, does it look like it's a linear function? Is there a constant change between each one of them? The fastest way to do that is to check, well, can I do my singular subtraction out? Is that constant? It's the same value each time, you know it's linear. If it's not, you try it again. If it doesn't work, you try it again. You only have to do this so many times to realize that it's not going to be some sort of or some sort of quadratic or polynomial model if none of them stays constant. Yes, sir?
Will we still have to do that even with like some crazy decimals like that? We just have to get.
It could still work. Yes, it could still work because you can still get a constant difference.
Okay.
Okay? Yes, ma'am?
Do we get calculators? Or like stupid calculators at least?
Probably.
Okay, good. 'Cause I'm really bad at adding.
We talked about this. Don't worry so much, okay? Now, if all that fails, then your next test is to go to your L1, L2, plot the natural logs of that to see if it's linear-ish. If it's linear-ish, then you know it's exponential, and you have to come up with the exponential model. Okay? It is pure when you're doing things like this. You're gonna have to have the calculator to check the natural log stuff, to check the if it's linear. Yes, ma'am.
Okay, if you were graphing to find out if it was linear-ish, couldn't you just like put the natural log and of the whatever number in L2?
You could, but then you'd have to retype what the original was to get the model. See what I'm saying? I would always, whenever I have a table, I would always go L1, L2, whether or not it's going to be exponential or logistic growth we talk tomorrow, or any of those polynomial ones, because you're always going to model it off of those two tables. The L3 is your variance one to check it. That's what you're checking with those. Yeah, Beth.
So we can't just go like straight to the calculator once, like we'll try it that way.
When you get to the test and stuff, that's what you'll want to be able to do. Tonight, it's exponential because it's in the exponential.
Like
that-
different like questions.
Right.
Okay.
I think that's what you're asking.
Like for like the exponential ones, when you're like showing work.
When you're showing, yeah, because then you could probably just use straight through your calculator and answer the questions. Okay? Does that make sense?
Yeah.
Okay. Any other questions?
So wait, do you have to write these?
Depends what the question asks you.
So
Because it might give you a table like this and then say, hey, estimate what year something was happening.
Something was happening.
Every year. So you like to quiz or test?
I don't know. I was trying to come up with something and it didn't work very well. So,
Estimate the number of Fridays, Olivia.
judging livestock.
Yeah.
It's a lame excuse.
It's like, okay, it came all the way
Are you giving this problem to do or are you giving this homework?
I'm giving you homework, but I'm just trying to show you this real quick. So, like, if you look here, where it says find the exponential model of the original data, estimate the cumulative number of stamps in the United States in the year 2000. you're going to be using that model to solve the question. That's what you wind up doing. So yeah, you're using it to solve for something that's something else.
So I have to write it for something else.
Sure.
I don't have to write work, I just have to.
You're quite the minimalist, aren't you?
Well, column, yes.
What page is this way?
I want to say it's
It's on page 513.
I thought Thomas just got up and like walked over there and started writing. For some reason, I don't know.
I have a third hour, so I can't.
Do those, please.
Oh, your book.
I thought you had gotten up because I just saw someone walk
I was thinking that.
in my aisle. And I thought you had gotten up and just started writing.
What was the category? Nut job? Doofus? What is my personality trait? I become more interested for independence and freedom. Enjoy my physical ability, enjoy using tools and objects. Natural performance for activities where shared activities and likes to explore new ways to energize my relationship with my animal. As a child, I had difficulties getting into academic routines. I learned more by doing experience than reading and listening. Needing physical involvement in the learning process was motivating and I found it fun.
That was the best.
Yeah.
I saw the last video starting summer next year.
Yeah.
Yeah.
The rest of the room.
Yeah, go ahead. Just leave the door open so you don't get locked out.
It's 26.